and y equals 0 if and only if y equals phi of x for all x and y is in belonging to IP. In other words, near P the constraint set C equals G equals 0 is in the graph phi. Note also that phi of x sub 0 equals y sub 0, reducing to one variable problem. Define the one variable problem function h from I sub p to r. H of x equals f of x and phi of x. This function records the values of f as we move along the constraint curve C near P. Since P equals x c sub 0, y sub 0 is a constrained extremum of f on x. The function h has a relative extremum at x equals x0. Since h is differentiable, this forces h prime of x0 equals works by reducing the constraint problem to an ordinary one variable problem, then translating the means geometrically. The key insight is this: if you are constrained to move along the curve g equals 0, and you are at a point where f achieves a maximum or minimum along that curve, then, just as in the unconstrained case, you cannot gain or lose anything from f by taking an infinitesimal step. The function h of x equals f of x and phi of x records that f does as you move along the curve, and prime h of x sub 0 equals 0 is a mathematical way of saying, now unpacking prime h of x sub 0 equals 0 via the chain rule and implicit function theorem, which tells us exactly how y must change with x to stay on the curve, yields a simple equation. A certain 2x2 determinant vanishes. In 2 dimensions, a determinant vanishes precisely when the two row vectors are parallel. So the condition prime h of x0 equals 0 is equivalent to saying gradient of f of p and gradient of g of p point in the same direction. Geometric picture: the level curve of f passing through p and the constraint curve g equals 0 are tangent at p. If they cross transversely, you can move slightly along g equals 0 to enter a region where f is larger or smaller, contradicting the extremum. Tangency forces the normals, the gradients, to be parallel. To find the constraint extreme of f of x and y subject to g of x and y equals 0, we must solve the system. The determinant of the gradient of f of p and the gradient of g of p equals 0, and g of x and y equals 0. The first equation encodes the collinearity condition. The second keeps us on the constraint. Together, they give a system of two equations in the two unknown x and y. All solutions are candidate for extrema. We must compare the values of f at each to identify which are maxima, which are minima, and which are neither. In dimensions higher than 2, the collinearity condition, determinant of gradient of f and gradient of g equals 0, generalizes to requiring that the cross product of the gradient vectors vanishes, or more generally, that the gradients are linearly dependent. equals 0. Gradients. Gradient of f equals 2x and 2y. Gradient of g equals 3 times x minus 1 squared and minus 2y. The collinearity condition determinant of gradient f and gradient g equals 0 gives determinant of this equals 2x times parentheses minus 2y minus 2y times 3x minus 1 squared equals minus 4xy minus 6y times x minus 1 squared equals 0. Factoring out minus 2y, it leaves us minus 2y times parentheses 3x squared minus 4x minus 3 parentheses equals 0. Case analysis: either y equals 0 or 3x squared minus 4x minus 3 equals 0. Check the discriminant of the quadratic. 16 minus 36 equals minus 20, which is less than 0. So 3x squared minus 4x minus plus 3 equals 0 has no real solutions. We must have y equals 0. Back to the constraint, substituting y equals 0 into x minus 1 to the exponent 3 minus y squared equals 0 gives x minus 1 to the third power equals 0. So x equals 1. The only candidate is 1, 0. Verification. The constraint curve passes through 1, 0. We can verify to satisfy 1 minus 1 minus 1 equals 0. Since the constraint set is not compact, we should also check that the distance does not approach 0 anywhere else, but the only branch of x minus 1 to the third power equals y squared near the origin is this one, and the curve goes to infinity in both directions, so the distance grows without bound elsewhere. Another problem. Find the maximum and minimal distance from the ellipsoid x squared plus 1/4 y x squared plus 1/9 z squared equals 1 to the origin. Setup: we minimize and maximize. F of x y z equals x squared plus y squared plus z squared. Square distance subject to the other. The constraint. The gradients are gradient of f 2x 2y to z. Gradient of g equals 2x half y and 2/9 z. Collinearity in R3. For two vectors in R3 to be collinear, their cross product must be 0. Computing gradient of f times cross product gradient of g equals 0 yields 3 scalar equations, one for each component. 2y times 2/9 z minus 2z times half y equals 0. So only if yz times 4/9 minus 1 equals minus 5/9 yz equals 0. So yz equals 0. Then 2z times 2x minus 2x times 2/9 z equals 0. Only if xz times minus 4 9 equals 0. That makes x z equals 0. And the same happens with x and y. Together, these three equations force any two of x, y, z to vanish simultaneously, combined with the ellipsoid constraint. The candidate points are 1, 0, function alpha itself is called the parameterization of the curve. A subtle importance observation: different functions can produce the same trace. For instance, the same circle can be parameterized at different angular speeds or in the opposite direction. This distinction becomes crucial when studying linear integrals, where we care not just about what the curve looks like, but about how it is traversed the function alpha, not just its image. The figure 2.1 shows a 3D coordinate system with axes x, y, z. A compact interval a, I lies on a separate real line, and the curve c winds through space. The function alpha maps I onto c. The label alpha equals parametrization is placed along the arrow from I to C, and C equals curve image of a label's trace. This visual illustrates that parametrization is a function from one dimension interval to the curve in space. Let I equals a p be a closed bounded interval in R, a continuous function alpha. I to Rn is called a continuous path in Rn. The path is called regular if the derivative prime alpha exists on I. Prime alpha of t is different from 0 for all t belong is in I. So this means the velocity never vanishes, and alpha, prime alpha is continuous on I. The path is called piecewise regular. If AB can be decomposed into finitely many subintervals, on each of which the path is regular, the non-regularity, if any, is confined to isolated breakpoints. The condition prime alpha of t is different from 0 is a smoothness condition. On the parametrization, it prevents the curve from having cusps or stops caused by the specific choice of parametrization, as opposed to the genuine geometric singularities of the curve itself. Physically, the velocity vector never points in all directions at once, never vanishes, so the motion has a well-defined direction at every instant. Simple curve. A curve is simple if it emits a C1 injective parametrization. This means the curve does not intersect itself. Each point on the trace corresponds to exactly one value of the parameter. A closed curve is closed if it emits a C1 parametrization from the interval 2 Rn with alpha of A equals alpha of B. The curve loops back to where it started. Simple closed curve. A curve is simple closed, a Jordan curve also called, if it admits a C1 parametrization. Alpha equals alpha from the interval 2 Rn with alpha of A equals alpha of B. That is injective on the interval AB. It closes up but would trace the same circle, but beta does so twice as fast. This illustrates the known uniqueness of parametrization. The same geometric object can be described by infinitely many different functions. Velocity, vector speed, and the tangent line. For alpha from I subset of R to Rn of class C1 written alpha of t equals alpha 1 of t tangent line. The point is L equals 365 plus t times 1 minus 1, 0 equals 3 plus t, 6 minus t, 5. Problem. A particle follows the curve. Alpha t equals e exponent t minus exponent minus t, and cosine of pi t, and leaves the curve along the tangent line at t equals 1. Where is it at t equals 3? Step 1. Compute position and velocity at t1. Alpha of 1 equals and minus 1. Prime alpha of t equals e of t minus e to exponent minus t. Prime alpha of 1 equals e minus c to the minus 1 and 0. Step 2. Write the tangent line. L of t equals e times a to the minus 1 plus t minus 1 times e minus e to the minus 1 and 0. And step 3 is evaluate at t equals 3. Equals 3 equals 3 plus 2 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 preserves orientation. If prime of I of S is lesser than 0 for all S belonging to J, the reparametrization is negative or decreasing, but it reverses orientation. Under these conditions, beta is regular if and only if alpha is, and beta of J equals alpha of I. This means they have the same trace. Now, the definition. Now, the figure for this definition shows two intervals I and J connected by the dimorphism phi from J to I. Both alpha from I and beta from J map to the same curve C in space with the relationship beta of S equals alpha of phi of S illustrated by arrows. This shows phi as a change of coordinates on the parameter space that leaves the geometric trace unchanged. When working with curves as point sets C, subsets of Rn, we restrict attention to curves that are traces of regular functions. This guarantees the existence of tangent lines at every point and allows us to study how the curve bends by analyzing how the tangent direction evolves. Any regular parametrization of C is equally valid as computation as 2. Caution. A curve C might be the image of both a regular and a non-regular parametrization. Example, the parabola C equals x y, where y equals x squared is the trace of both alpha t of t equals t and t squared regular, since prime of alpha of t is 1 and 2t, which is different from 0 for all t, and beta of t equals t to the 3 and t to the 6, which is not regular, since beta prime beta of 0 equals 0 and 0. The non-regular parametrization beta cannot be used to compute the tangent line at the origin. Even though the curve has a perfectly well-defined tangent there, the tangent at the origin of the parabola is the x-axis. Recoverable only from alpha. A positive increasing reparametrization traverses the curve in the same direction as the original parametrization. The orientation, the sense in which the curve is traveled, is preserved. A negative decreasing reparametrization traverses the curve in the opposite direction. The orientation is reversed. All other geometric properties which points lie on the curve, the shape of the trace, tangent direction as geometric objects are unchanged. The figure shows two side-by-side diagrams showing the same curve C. In the left diagram, alpha and the positive reparametrization beta both traverse C from left to right, same arrows. In the right diagram, a negative reparametrization beta reverses the direction. The arrows on C now point depend on the choice of parametrization. It is a property of the curve as a geometric object, not of how it is described. Let alpha from I to R3 be a parametric curve, and the interval and A to be a subset of I. We want to compute the length of the arc traced by alpha between alpha of A and alpha of B. The length of alpha from A to B. Motivation. Describe polygonal specify the arc length of the arc alpha of the interval a to b is L of b to a of alpha, which is equal to the integral from b to a of the norm of prime alpha of t dt in R3 with alpha of t equals x of t, y of t, z of t, then the norm is the root of prime x of t squared plus y prime of t squared plus z prime of t squared dt in R2 with a t equals xt and yt, then it is the norm. The norm is the root of prime x of t squared plus y prime y of t squared. Basic examples. Straight line segment for alpha t equals p plus dv with v different from 0. This p is the norm, which is equal to v constant. So the integral will be the integral from b to a of from a to b, the norm of v dt, which is equal to the norm of b minus a, which is equal to the norm of a of b minus a of a alpha. Oh no, alpha of b minus alpha of a. As expected, the length of a straight line segment is just distance between its endpoints. For a circle, for alpha t equals b0 plus r cosine of t sine of t, the speed is prime. The norm of prime alpha of t equals r constant. In the interval 0 to 2 pi, alpha makes exactly one full revolution around the circle. Its length L from 2p to 0 of a equals the integral from 0 to 2 pi of the norm of r dt, which is equal to 2 pi of r. This is standard circumference formula. Note, if alpha runs over 0 to 4 pi, it makes 2 full revolutions and gives length 4 pi r. Same trace, double the length. The arc length depends on the interval, not just the trace. Graph of the function for alpha of t equals t phi of t. Parameterizing the graph of phi, the speed is root of 1 plus prime phi of t squared. Therefore, the length is the integral from a to b of root of 1 plus prime phi of t squared dt, which is the classical arc length formula for graphs of function. Problem: find the arc length of the helix. Draw. Pro t Let C be a curve with parametrization alpha from I to Rn, and let beta from J to Rn be a parametrization by the diffeomorphism phi from J to I, so that beta equals the dot product of alpha and phi. Then the length of the curve when beta is the same as the one of alpha. Since beta equals the product, the chain rule gives prime beta of S equals prime alpha of phi of S times prime phi of S. Therefore, the norm of prime beta of S equals the norm of prime alpha of phi of S times the absolute value of phi of S prime, integrating over Ct, which is the interval 8b over phi, the inverse. Then the length of Ct of beta equals the interval from C to D of the norm of B prime of S ds equals the interval from C to D of the norm of prime alpha. Prime alpha of V of S times the absolute value of prime phi of S. Apply the change of variable theorem with the substitution t equals phi of S dt equals prime phi of S ds. Since phi is a diffeomorphism, so prime phi does not change sign. D norm phi of S times ds equals dt, and the limit transforms as S. It belongs to the interval C, D. If and only if D belongs to the interval A to B. So the intuitive explanation is, if you walk the same road, regardless of whether you walk it fast, slow, or in reverse, you always cover the same total distance. This is what the lemma says. The arc length of the geometric curve C is a property of C itself, not of how it is parametrized. The mathematical reason this works is that the norm of prime phi of S appears both in the speed of beta, making beta faster or slower, and in the change of variables factor of the integral, compressing or stretching the S element. These two effects cancel each other exactly, leaving the integral unchanged. Definition: arc length of a curve for parametrizable curve C with injective C1 parametrization from AB to Rn. The arc length of C is L of C equals L from A to B of alpha equals the integral from A to B of the norm subset of R2Rn, the following hold. Product rule for even products. Rn equals 3. Product rule for cross product. Derivative of the norm. shows